Let me share my screen with you. And then we'll take the exam, okay? Uh, after finishing this part, I will post the exam and to take it, okay?
Hey, Professor.
Yes.
I think the homework that was due last night or whenever, I
Mhm.
think it had stuff that we didn't talk about yet on the homework.
Uh, what's your code? What's your code number?
Me? 3.
Mhm. 3. Okay. Uh,
I mean,
no,
I
the only part left. Do you see the screen?
yeah.
This is the only part left. But if you're talking about the question with T, the truth table,
Yeah.
no, it's given here. This is the same example here.
Yeah, I just had to like Google like a
Determine standard expression from a truth table. Here we are. Here is asked for standard expression, but in the question simplify the expression. So, but how you get the expression? You get it like this one exactly. But after you get this form, you simplify. Simplify it using the Boolean algebra we mentioned here. Simplify it using this Boolean algebra.
yeah, I was just saying like when you
Yeah, the
simplify it,
same.
there's
The last expression when you get it, when you get the last expression, you have a term like just 1 second to show you. You have a term similar to this, so you can simplify it using this or this, similar to one of these here. I don't remember exactly, but you will have a term. You can simplify similar something is similar like this or this, so you can simplify. But is typically like this one. The example, the question is very similar to this one. You have the truth table. You have y or the output. You have zeros and ones. How will you get the terms or the product terms? Just choose the ones, circle the ones, and they get F1, F2, and they then add them up. This gives you the standard expression. But after you get that, what we need in the homework, just to simplify this expression. How we simplify it using Boolean algebra, like we mentioned before. Okay? So there, and the only part left is this one here. Everyone see what I'm saying? If if you need extra time for the homework, I can do that. So do you need extension for the homework?
no, I'm okay. I did it. I was just saying it.
Mm. Anyone ask for extension for the homework? Let us extend it like another 2 days, okay? For homework too.
That
So
sounds good.
if you have anything, you can resubmit, and I will make sure that you have 2 attempts to submit. Okay,
Thank you.
you will. But it's very similar to here. Okay, you see what I'm saying? The one who asked it, Joshua, I think Joshua asked it.
Yeah. Yeah, I
So
got it.
yeah, okay, good. Now, let us go ahead and, as I mentioned, after we finish this portion, uh, just give me like 2 minutes to post the exam. Okay. Everyone is good today?
Yeah.
Everyone is okay? Yeah, be careful is extreme weather heat outside, so you have to be careful. Okay. Um, okay. So I mean, this in sorry, this in Fairfax area. Okay. 3 and 2 level implementation. So yeah, this is something related to the design. Sometimes it's required 3 level, sometimes 2 levels. So what is the difference? For 3 level, look at maximum number of gates starting from the input, like D and E inputs. Everyone sees the screen.
Yes.
Yes.
Like if we go from D and E inputs up to Y, so how many gates we pass through? This OR gate and the gate and then OR gate. So, but the other one, A and B, is just 2. So we consider 3. So this is called 3 level implementation. And in this case, if we are given Y equal AB plus C multiplied by D plus E, and to draw the circuit, as we mentioned, we start with Y, the output, and to go back step by step until we reach to the input. So we know this is sum of product term. We have AB product term, C multiplied by D plus E product term, and then they added logic addition. So this sum of product. So sum of product is, as we mentioned, is the output of OR gate, because we have logic addition between the terms here. So this means the output gate is OR gate. Then we have AB plus C multiplied by D plus E. So this means one term is AB, so one input is AB. The other input is C multiplied by D plus E. So the other input C multiplied by D plus E. AB, this is the output of AND gate or OR gate. What do you think? AB. And who says that? What's your code?
Number 1.
Number 1. Perfect. Number 1. Thank you, number 1. You are number 1. Okay, good. Why you mention AND gate? Why you said AB is the output of AND gate? Why?
It's multiplication.
Okay. I wish to hear to answer me, but that's fine. What's your code, sir?
23.
23. Thank you, Gabriel. Gabriel?
Yes, sir.
Oh, okay.
Yeah.
Yeah, as he mentioned, because AB is logic multiplication, A multiplied by B. So this is the output of AND gate. So the output of AND gate is AB, so one input is A and the other input is B. We reach to the original inputs, because if we have A inverted B, so one input is A inverted and the other input is B, then A inverted is the output of, if we have A inverted. So this will be the output of what? If say this A is A inverted, so we have another gate, right? What is the gate to reach to A?
NOT gate.
Not gate. Perfect. What's your code, sir?
7.
7. Same people. Same people, almost. Thank you, sir. Thank you. Exactly. And the same thing for the other input. The other input for the OR gate is C multiplied by D plus E. So this is multiplication of C and D plus E. So this is the output of AND gate. This AND gate, one input is C, the other input is D plus E. This D plus E input is the output of OR gate because you have logic addition here. So OR gate with two inputs, one input is D and the other input is E. Is this clear for everyone? If we have the output, sorry. If we are given the Boolean expression, which is the output function, can we draw the circuit like this? Can we draw the circuit, guys, or it's not clear? Just one said yes. What about the others?
Makes sense.
Okay.
Yeah.
Okay, good. For two-level implementation, as you can see, the maximum number of gates, if we start from the inputs to the output function or Boolean function, is just 2 gates. So if you go from A and B to Y, so just 2 gates, or any other inputs, it's just 2 gates. So this is called the two-level implementation. This is a table for all logic gates we use. All gates we use in our digital design is listed here with their inputs and out, with their truth table. Everyone sees this?
Yes.
So AND gate, logic multiplication. So Y, here the output is F. The input is X and Y. It doesn't matter. It's just variables, notations we use. So F equal XY. And this is the truth table. 0, 0 is 0, 0, 1 is 0. This logic multiplication. 1, 0 is 0, 1, 1 is 1. OR gate, F equal X plus Y. And this is the truth table. NOT gate, the input X, if the input is X, F is X inverted, or X not. This is NAND gate. This is called the NAND gate. What is the difference between AND gate and the NAND gate? What is the difference you see?
The NAND gate has only there's only one way to get a 1 in the NAND gate.
As a symbol, what is the difference?
The NAND gate is 1 unless both are on.
What is that?
I mean, it's just the reverse of the AND gate. If both are on, then it's 0.
In the symbol itself, what is the difference?
Invert bubble.
There's a bubble.
Is this AND or NAND?
Is inverted. There's a NOT gate.
As a function, yes, but as a symbol, what is the difference?
There's a
The bubble. The bubble.
Yeah, is this bubble here? You see this bubble, this circle here? Who said bubble?
20 and someone else.
20?
And 7.
And who's the someone else?
7.
2.
What's your code?
I
What's
said 7. Someone else said 2.
7 and 2?
Yeah.
Okay, fine. Thank you. Yeah, we have bubble here. Bubble is this circle here at the output. It's called the bubble. So if you look at and NAND, I mean AND gate, comparing to NAND, and there is no bubble. And there is a bubble. This bubble which make us call it NAND. The first N, the first letter N means negative or invert. Invert the output of AND. So the best way to deal with this, if you need like the truth table, do the truth table for AND, the regular AND, and then invert the out. So as expression for AND, Y equal AB, but this is NAND, so is AB inverted. Total AB inverted, not A inverted, B inverted. We mentioned last time, AB total inverted does not equal A inverted, B inverted. Does not equal. They are not equal. So for the truth table here, X and Y 0, 0 for AND, you can open other column here. You can open other column here. So 0, 0, put 0. 0, 1, put 0. 1, 0, put 0. 1, 1, put 1. And then the last column, which is the output F, invert what you got. So 0 inverted to 1, 0 inverted to 1, 0 inverted to 1 inverted to 0. Okay, if you worry about any confusion, just do it for AND, and then take the invert of the output. Everyone see what I'm saying? Please, if anything is not clear, ask. Ask, please. Don't leave it. Okay. Then NOR gate, the same thing. NOR gate is the main difference between OR and the NOR is the bubble at the output here, the circle. So if you look at OR, there is no bubble. But OR is bubble. NOR is, we have a bubble here. And it's the same thing. Is the output of OR gate inverted? So we mentioned the output of the OR gate, OR, not NOR, OR, is just a logic addition. So X plus Y. For NOR is X plus Y total inverted. Means the inverted sign is over the whole term. X plus Y inverted. Do you see this expression? You can write it like this, or you can put a bar for everything. This is the same thing. We put X and Y as one unit inside the practice, as one package, and then we put invert at the end. The same thing. What is this? What is this gate here? What do we call this gate? The next gate. What we call it? Anyone has idea? Exclusive OR. Exclusive OR. Of course, all gates are important because we use all of them in our design, digital design. But this gate, especially this gate, is very important gate because we use it in huge applications. We use it in encryption. We use it in encoding schemes like frequency hop, like direct sequence, split spectrum techniques in communication systems to encode the signal. It has a lot of applications. So this is very important gate, exclusive OR, XOR, either exclusive OR, you can write it XOR. So what is the function of this exclusive OR? The expression is F. You see this expression here? F equal X or exclusive OR X and Y, or X exclusive OR Y. And the symbol for exclusive OR is, as you see, this circle, and inside this circle, there is plus sign. This equal to what? This equal to x, y dash, y inverted, plus y, x inverted y. This what this expression equal to? X exclusive OR y equal xy inverted plus x inverted y. But we can summarize the function of this gate in one statement. What is this? Similar inputs gives 0 at the output. Means if x and y are the same, either 0, 0 or 1, 1, the output will be 0. If they are different, like x is 1, y is 0, or x is 0, y is 1, the output is 1. So this simple statement summarize the function of this exclusive or summarize this equation here. We never, to get the output of the exclusive OR, yeah, this is the mathematical expression if we need it for other purposes. But as a function in the circuit, for this gate, just to look at similar inputs, the output is 0. The two inputs are different, the output is 1. And you can see here in the truth table, 0, 0 is 0, 1, 1 is 0, the output, I mean. If the input 0, 0, F is 0. If the input 1, 1, the output is 0. But 0, 1 or 1, 0, the output is 1. Please, is this clear for everyone? Or anyone has confusion here?
It's clear.
It's clear.
Clear for everyone?
It's clear.
Okay, good. Exclusive NOR. This exclusive OR, but the next one is the exclusive NOR. So what is the difference? The bubble here. The bubble here. Same thing, and this is the function mathematically. Sometimes we need the mathematical function to solve certain problems, okay? But if this inserted in a circuit and we need to know what is the output is logic high or logic low, so we just to go through the function of each gate, like we mentioned. And when we reach to this exclusive OR, as I mentioned, if the two inputs are similar for this one, if the two inputs are the same, 0, 0 or 1, 1, so the output is 0. If 1, 0, 0, 1, the output is 1. Exclusive NOR, the same thing, just if the same thing for exclusive OR, but invert the output after that. So for example, for this one here, exclusive NOR, assume first exclusive OR, so 0, 0 is 0, and then invert 0 to 1. So 0, 0 for exclusive OR is 0. For exclusive NOR, just invert the output to 1. Okay? And the rest, same approach. Any question with the gates? This all gates we use in our digital design. Is listed in this table here.
Professor,
Yes, yes, sir.
for the last gate, isn't this just
For
some
what?
gate?
Which gate?
For the last gate.
Not gate, do you mean?
The last one.
The last one here?
Isn't
This-
this
This
just
one?
last AND gate?
This one?
Yeah.
Okay. Yeah, what's the question?
Isn't this just same as AND gate?
I don't hear you.
It works just like AND gate.
This is exclusive NOR. This
Oh,
is
sorry, I
the
made a
function
mistake. Never mind.
of
Yeah.
exclusive NOR.
Yeah, I made a mistake. Never mind.
No, each gate has different function.
Yeah.
Any one of these gates has different function. Maybe have like 1 or 2 lines is the same, but never be everything is the same.
Yeah.
Has different functions. That's why we use it for different stages in the design. Okay?
I have one question.
Yeah, go ahead.
If you so the zero is low, so if there's no current, is the zero current and one is like is zero no current and one is current flowing, right? Can I think of it that way?
We talk about the voltage levels actually.
Mhm.
Okay? So when we say logic high means as we did in the lab. Okay. This is a good point. You reminded me of something I need to talk about it. When you did the lab, to connect the switch to logic high, what you did? You connected to what?
The voltage source, or I connected
Exactly.
it to
You connected to 5 volt, right?
Mhm.
The VCC we use is 5 volt. So when you connect the input to logic high, you connect this switch to 5 volt. When you insert the input 0 to the gate, you connect this input to the ground, which is 0 volt, right?
Yeah.
So of course, voltage and the current, they are related, but when we say logic high or logic low, we specifically talk about the voltage levels, as we mentioned, and we'll talk about it here also. Positive and the negative logic systems. So in the design, most likely we use for logic high or we use bit 1 for logic high and bit 0 for logic low. This like most like 95% in the design. But sometimes we have to use the reverse. Means sometimes we use bit 0 for logic high, bit 1 for logic low.
Okay.
For design purposes. Okay. So if we use bit 1 for logic high and bit 0 for logic low, as you see here, this is called positive logic. If we use 0, bit 0 for logic high and bit 1 for logic low, this is called the negative logic. The point here is don't be astonished or confused if you see in certain design when you are given the input stream of bits, so you may see logic 0 represent logic high, bit 0 represent logic high, bit 1 represent logic low, which is just like different than we usually use. So it's not wrong. It's okay. It can be. I mean, it can be used like this. Okay. Digital logic families. As this, we talk about the technologies used here for manufacturing these logic families or logic gates or logic ICs, digital ICs. So we use TTL. This is technology. It's called TTL, and they call it also logic family. Which TTL stands for transistor logic. Transistor logic. And the kind of transistor we use here is semiconductor manufacturing. It's called the bipolar junction transistor, like the one we draw when we discussed the inverter, like base collector emitter. It's called the bipolar junction transistor. This family is like a standard family, and it has high speed. It is the operating or the processing of these gates is high. It has high speed. High speed of operation. But the power consumption is high. For TTL, the power consumption is high. However, MOS or CMOS, MOS stands for metal oxide semiconductor. CMOS is the same, almost the same. It's complementary metal oxide semiconductor. These MOS and CMOS we use field effect transistors, another semiconductor manufacturing. It's called field effect transistor. So instead of the base, we have the gate. Instead of the collector, we have drain. Instead of the emitter, we have the source. So different symbols for either TTL or CMOS. This MOS or CMOS, it is lower speed as operation. Like for example, what I mean by this, like you apply the input, you get the output for the circuit after 1 second, for example. However, in TTL, for the same circuit, number of gates, as the input, you apply the input, you get the output at like half of 1 second, for example. So this is faster operation, faster processing for the data inside the circuit. So TTL is faster, CMOS is slower, but TTL has power consumption, high power consumption. CMOS has low power consumption. This is important. High speed is important, and also power consumption is important. So if you are not worried about power consumption and you need faster operation, so you use TTL. If you are worried about power, like for what? For military applications. For military applications, we need always faster operations. So in military, specifically in military, we rely on another technology. It's called ECL. ECL is emitter coupled logic. This is more high speed operation. But generally speaking, if I'm looking or my concern about high speed, and I don't worry about the power consumption, so we use CTL. Like as I mentioned, for military application. And if power consumption is my concern and high speed is not, I am not worried about it, but I am worried about power consumption, so we use CMOS. And this actually, the main application for CMOS, we use it in logic encryption. In logic encryption. In encrypting the circuit itself. So like we have, say, for example, this circuit here, we can encrypt this circuit. So like if someone steal the circuit or the system, you know, they use reverse engineering to know what is the system, how it works, and what is the function. So if we encrypt the circuit inside, it's hard to, if they use reverse engineering, it's very hard to discover how this system works. So we put keys here actually inside the circuit here. Either we encrypt the circuit on the gate level, like this gate here, I encrypt the gate, or inside the gate itself, we encrypt the transistors. So the only one can make this circuit work properly is the authorized person who knows the keys. Other than this, like people, as I mentioned, steal the system or the circuit and try to go use reverse engineering to know what is the function. For example, if this is the OR gate here, I don't know what is this gate. I don't know what is the function. I steal the system and I don't know the layout of the circuit. But if apply 1 and 0 here, the output is 1. If apply 0, 0, the output is 0. 0, 1, the output is 1. 1, 1, the output is 1. So immediately I know this is OR gate without having the IC number or any information about the gate. From the input and the output functions, and we know the truth table, of course, we can know what is the gate. But if I encrypt this gate, if I don't know the key of the encryption, if I put 1 and 0, I get something else. I don't get 1. Or if I get 1 this time, when applies, if say 1 and 0, I got 1, for example. But if apply 0 and 1, I get something else. So this confuse me. So I can't know what is this gate. Why? Because it is encrypted. Okay. So this actually we use CMOS technology. I mean, the family of CMOS for this purpose. I mean, one of the application, of course, to encrypt or logic design encryption or cybersecurity in logic design.
Professor,
Yes, sir.
someone is in the waiting room.
Someone is out.
Yeah.
I have everyone in the class at the beginning, so someone go out. Stephen. Stephen, please stay in the class, okay? Don't interrupt the class, please. Okay?
Also, I have a question.
Yes, go ahead.
How does the encryption work? Like, how can a gate produce different results if you don't have?
I can, okay, if we have time, I can talk with you a little more about this, okay? So
Okay.
I can show you a circuit and show what exactly happens, okay?
Sure, after class if we have time. Thank you.
Okay. Integrated circuits, the ICs, integrated circuit is a number. You know, when you see, when you look at IC, everyone knows how the IC looks like. Chip,
I've seen those 555 timers.
yeah, something, yeah, similar to this. So this IC actually is like for the lab. When we did the lab, we did for OR gate and the gate and the NOR gate, or and O and not gate. Inverter, we did the lab for inverter to verify the function of NOT gate, to verify the function of AND gate, to verify the function of OR gate. So we use the IC for each gate. So we use the IC. And in the lab, we look at inside the IC. So we saw number of gates inside. All right. Well, let me remind you with what we did, just to remember. Okay. Everyone sees this, the lab before? We did before? Do you see the lab document?
Yeah.
You see, this is the IC here. This is the IC. So what inside the IC? Gates, right? Right? So
Yes.
this is the IC for OR gate, which the number is, I mean, for NOT gate, which the number is 7404. I mentioned, don't worry about the letters inside the number, but the number 7404. And this actually, as I mentioned before, 74 indicates that this TTL technology, any TTL technology, IC based on TTL technology, start with 74. For CMOS, start with C letter. But any TTL is 74. So this is the IC, simply this is the IC. So what is the IC? Is the number of gates, is a number of gates inside the chip. Okay? So an integrated circuit is a number of logic gates fabricated on a single silicon chip. ICs can be classified based on how many gates they contain. So each IC has certain number of gates. And based on this number, we say this is a small scale integration, medium scale integration, large scale integration, or very large VLSI, and so on. So for small scale integration, if the number of gates inside the IC less than 10 gates, it's called the small scale integration. Medium scale, like what? For small scale, like the ICs we just talk about in the lab. Not gate, or gates, and gates. A medium scale between 1,000 and less than 1,000 and more than 10 gates. Like what? Registers, counters, decoders. We will talk about this later. Large scale between 1 million and greater than 1,000, like memories. The IC is used for memories. Very large scale integration is around 1 million gates inside. 1 million gates. Imagine this. Like what? Microprocessors. Ultra large scale integration, more than 1 million. More than 1 million is called ultra large scale integration. Like more advanced microprocessors and more advanced memory ICs. Okay. Any question? Any questions? Guys, any questions?
I don't have any questions at the moment.
Please, if you have question, ask. If you don't, so just let me hear. You are okay, okay? Okay, now let us take like 3 minutes break, and I will post the quiz, okay? Okay, so just give me 3 minutes or so to post the quiz, okay? Mhm.
Professor, I have a question.
Give me 1 minute, please. 1 minute. Just 1 minute. Let me finish this, please. Okay. Okay. Now you should see the quiz. So just to go ahead. If you have any issue, tell me, please. Okay. Or if you have any question about the quiz.
The quiz isn't open yet.
It should be okay now.
I don't see it also.
I see it, but it says this assignment is part of an unpublished module. It is not available.
Okay, hold on.
It says
Let
it
me
says it's only going to be
see.
available at 4:30.
Okay, so let me see. Oh, okay.
It says due at 4:30.
Just 1 second, please. Just 1 second. Okay, let me. Yeah, you are right. Sorry. Okay. Now you can see it. Can you see it now?
Yeah, I see it.
Okay, go ahead, please. Try to finish before 4:30. But if you need more time, let me know. Okay.
Okay.
Okay. Yes. Someone has question. You
I
mentioned
have a quick question about the syllabus schedule.
the syllabus.
Is our midterm still going to be on July 1st?
I will tell you about the exams. Most likely will be shifted. Most likely will be shifted. But before any exam, as I mentioned, I will tell you.
All right, thank you.
Okay. And Hamza, do you hear me? Hamza?
Yes, Professor, I'm here.
Hamza, you must give me the percentage of each member in participation of each member in your group.
Okay, I will send you an email. I will send you an email about that.
Yeah, please. And put this in each.
Yeah, I forget
After
about
that,
it.
you need to put this to include this in the report. Okay.
Okay, sorry about that.
Okay, that's fine.
Professor, I have a question. Do we have to
David,
stay in the class?
hold 1 second, please. David Ephraim. David Ephraim, do you hear me? David Ephraim, if I'm right. David, do you hear me? Okay. Yes, sir. Go ahead. The one has question, please go ahead.
Oh yeah, do we have to stay in the class? Or can we just
What
leave
is
in
that?
Zoom? Do we have to stay in the class? In the Zoom meeting?
I don't hear you. I'm sorry.
Do we have to stay in the Zoom meeting?
I still not hear you. What was the question? After you finish the quiz, you can leave. Is this what you're asking for? The one.
Yeah, I think that he was asking
Mm.
if he needed to stay in the class while he took
No,
the
no,
quiz.
no. After you finish the quiz, but make sure you submit everything right, okay? So you can leave after you finish. We don't have lecture after the quiz. If this does not answer your question, please chat with me. Okay. Sometimes, you know, some people has echo on their phones, so I don't hear them well. Okay. Okay, good luck, everyone. Go ahead.
Hey, Professor, you call my name.
What is that?
You call my name, David Ephraim.
Oh. Yes. I will chat with you, okay?
Okay, that's fine.
Mm. Okay, David, let us talk after you finish the exam, okay?
Okay, Professor.
So
That's
please,
fine.
please stay after you finish.
Okay.
Professor,
Yes, ma'am.
I had a really quick question, about question 2 on the quiz.
Question 2 in the quiz.
Mhm.
Okay, let me-
Um,
just 1 second, please.
mhm.
Question 2, yes, ma'am.
I was wondering, was it on purpose that C is always equal to 0 in the chart?
Can you speak loudly, please?
Yes, I'm sorry. I said, was it on purpose that C is always equal to 0 in the chart? Or should it also have
You talk
values of
about the C input.
Mhm.
C input is always 0 because connected to the ground.
Oh, okay, I see.
Mhm.
All right, my bad. Thank you.
You're welcome.
Professor,
Yes, sir.
for question 5,
Question 5.
is that already in the two's complement form, or do we have to convert it?
What is that?
Is the number that's given already in the two's complement form, or do we have to convert it first?
We need to subtract these two numbers, these two binary numbers, using two's complement form. This means you need to put the second number here, which is negative, in two's complement form, and then carry out the subtraction. Exactly like we did in the class. This is very similar, except of course different numbers.
All right, thank you.
Mhm. Okay, homework 2, guys, is extended for June 26th.
About the extension, does that mean we can also resubmit the assignment?
Yeah, you can resubmit. I added one more attempt.
Thank you.
Mhm.
Professor,
Yes, sir.
if I'm done, can I leave?
Yeah, yeah. But make sure everything is okay before you leave. Your submission is okay, everything is okay. Okay?
I already submitted it. So
Okay, good.
I checked
Have a
it
good
though.
day. Take care.
Thank you, Professor. Have a good day.
You too. Take care.
Professor, did you get code 10 for the attendance?
What is that?
Did you get code 10 for the attendance?
Yeah, everyone is here.
Okay, thank you very much. Have a good day.
You too, take care.
Professor,
Yes, sir.
did you see the message I sent in the chat?
Just 1 second, please. Yeah, we'll talk later, Chen. We'll talk later, okay?
Okay, next time. Yeah, thank you.
Okay, so if you're done, you can go, okay?
Okay.
Professor,
Yes, sir.
in question 4, do we need to write the whole output or just the answer?
And question 4,
Yes.
just to convert the binary number to gray code.
Okay. Got it.
Yeah.
Have a good day, Professor.
You too. Take care.
Have a good one.
You too. Take care. Bye.